Hello, dear students. Welcome to our new class. I hope you're all doing good. So before I start, if you remember in the previous classes, we have learned about motion of an object, the different factors that affect the motion, and the forces that act upon it while it is in motion, and gravitational force, things like that, and all the terms and scientific phenomena based on the motion of an object, right? So, in this class, we are going to learn how this force or how the motion of an object is related to the work, power, and energy. So, before I start, I would like to ask you one thing. So, what is that thing that come into your mind when you hear the word or the term work? Can you answer me? What is the first thing that come into your mind? Yeah, you might be thinking about the your parents, your mom and dad going for work every day, or you might be thinking about your parents and teachers telling you continuously about working hard to get good marks, or you might be thinking about some physical work that you are doing. Right. So all these things come into your mind when you think about the word work. So, in daily life, all these come under the term work. But in physics, some of these might not be considered as work. So, that's what we are going to learn first. That is, according to physics, what is work? All right. So before we go to the definition and the scientific terminology and all, first I would like to show you four scenarios, and I want you to look at it and tell me which of them are considered, in which of those scenarios work is said to be done. All right. So I'll show you here. You can see four pictures. So the first picture, a man is pushing a wall so hard, but it's a huge wall, so it's not going to move. Anyway, he's trying so hard, pushing the wall for hours and hours. All right, so you can see that frustration in his face. So he's trying that hard, right? And in the second picture, you can see a person is pushing a cart. So he's pushing the cart from one place to another along the road, right? You can see that, right? So that is the second one. And the third one, you can see that a woman, she is lifting weight. So she is participating in some kind of weightlifting championship. So she is lifting weight. So that is the third scenario. And in the fourth one, you can see a person holding a box like this and walking, right? So you have these four pictures here. So can you tell me in which of these cases work is done? Which of these people have done work while doing these? It may be all the four or it may be just one. You can just give a try. All right. So you think in all these cases work is done? But then I'll say no. That's where we want to learn what is work according to physics. All right. So in physics, for work to be done, a force should be applied. All right. For a work to be done, you should apply a force. But that is not enough for a work to be done on an object. Along with the force, the object should move in the direction of force. So if you are trying to push some object like this, so that object should move in the same direction with this force. All right. So there should be a force and a displacement, right? There should be a force and a displacement for a work to be done on an object, which is very important. So if there is no force, then there won't be work done. And if there is no displacement, even if a force is applied, there won't be any work done. So you understand, for a work to be done, there should be force and displacement. So how do we calculate work then? Work is equal to force into displacement. Force multiplied by displacement gives you work done on that object or by the person or whoever it is. Okay, so in definition, work done is defined as the product of magnitude of the applied force and the displacement caused. And this applied force and displacement is not just enough. The force should be in the direction of that force. I mean, the displacement should be in the direction of that force. Do you understand? And the SI unit. So you already know the unit of force and displacement. You have learned it in the previous chapters. So what is the unit of force? Unit of force is Newton, and unit of displacement is meter. So Newton meter, which in SI unit, this Newton meter is joule. All right, joule. So now we can go back to in earlier scenarios, you can have a look. Now you can tell me in which of these cases work is done. So this man is applying a force. He is applying a force in this direction, right? He's applying a force. He's trying so hard. He's tired. He's been pushing the wall for hours and he's tired. But that doesn't matter. Is there any displacement there? Has the wall moved at least a bit? No. Oh, poor man. The displacement here is 0. So the work done here is 0. Even though he pushed that hard for hours, the work done by him on the wall is 0 because there is no displacement here. So I think you understand, you get an idea of what is work done according to physics. Now we can look at the second case. Here, the man is applying a force in this direction to push the cart. And we know that the cart is moving in the same direction. So there is a displacement there. All right. So there is a force there and a displacement. So we can say that the man has done some work. All right. There is force and displacement, and the displacement is in the direction, same direction as that of the force applied. So in this case, work is done, right? And this third case, look at this. So this woman, she is applying a force in the upward direction. And you can see that the weight is moving in the same direction as that of the applied force. So force is applying upwards and the weight is also moving upwards. So you can say that here also there is a work done. Very good. Now the fourth case. You can see that this person is holding the box. So he is applying a force upward, right, on the box, right? With his hands, he is applying a force upward, right? But look at the box. While the man is walking, the box is moving in this direction. So force is upwards But the displacement, even though there is a displacement, the direction of the displacement is perpendicular to that of the applied force. So here work done is 0. No work done. But there is another scenario we have to consider here, because before he carry this box, he have taken the box from the ground, right? So he have applied a force while he was taking the box from the ground. He had applied a force and push it upwards, right? So in that case, while he was picking the box and taking it up, he applied a force in upward direction and the box have also moved upwards. So initially he have done a work here, but while he is walking, he is not doing any work. So with all these different scenarios, you might have got a very good understanding of what is a work done according to physics, right? Very good. So now you'll be able to, do any cases. You can figure out if a work is done or not, right? Very good. All right. Now, let's move on to the next slide. A numerical problem based on, it's very simple. So you can see that a force of 5 Newton is acting on an object. Let's see. So here you have an object, right? Suppose it's mass with a mass m. So a force is force of 5 Newton. 5 Newton force is acting on this object. So what happens? The object is displaced through 2 meters in the direction of the force. So the object moves in the same direction as that of the applied force. It is given here in the direction of the force. So this object moves in the same direction. How much displacement? 2 meters. So if the force acts on the object all through the displacement, what is the work done? So what is work done? Work done is force into displacement. So we know force is 5 Newton and displacement is 2 meters. So we know work done will be 10 Newton meter, which is 10 joule. Very easy, right? All right. So let's see what comes next. So we know what is work done. So the next one is energy. So for a work to be done, what is required for a work to be done? What is required for a work to be done? Yes, you need energy to do work. You need energy to do work. That's why your mom from your childhood onwards, she is always telling you, eat food, then only you will get energy, then only you will be able to do work, right? She'll be continuously telling this every day for every meal, right? Why? Because when you eat food, you will get energy, and with that energy, you will be able to do work. So for a work to be done, you need energy. So what is energy? Energy is the capacity or ability to do work, right? For a work to be done, you need energy. So energy is the ability to do work. And so we know that this energy that we have is actually converted into or making use of as work, right? So the SI unit of energy is also joule, because your energy is getting converted to work, right? So the SI unit of energy is same as the SI unit of work, which is joule. Object that does the energy does the work loses energy, and the object on which the work is done gains energy. You will get a perfect idea while we discuss it further. Okay. So from all this, what do we understand? If an object possesses an energy, it can do work. So they are very interconnected. Work is done only when there is energy. They are very much correlated, or work can be done only if there is enough energy. Do you understand? All right. So there are like different forms of energy. First one is mechanical energy. What is mechanical energy? Can you give me some example? Yes, car moving, your fan rotating, right? So all these kinds of energy are mechanical energy. Next one is heat energy. What is an example of heat energy? Yes, your iron box, right? We are plugging it, switch on. So there is an electrical energy which is getting converted to heat energy because the iron box getting heat up. So electrical energy is there. It is converted to heat energy there. All right. Next, we have chemical energy in batteries. Energy is stored. So that is chemical energy. And electrical energy. So electrical energy, as I've already said, while we said about the iron box, first we are using electrical energy. While you are turning on the television, all your electrical equipments, we are using electrical energy. Light energy. What is the light? The primary source of energy, we know that it is sun. That itself is giving out light energy. And the bulbs we are using in our homes, they are giving out light energy. So there are several other forms of energies as well. So you can go through it. So in this chapter, we are discussing more about the mechanical energy. So mechanical energy is actually the total energy on an object due to its position and or its motion. The total energy an object has due to its position or its motion. So we have two types of mechanical energy. The first one is potential energy. What is potential energy? So we said there is an energy due to position. That is actually connected with the potential energy. Potential energy is actually a stored energy of position. So it depends upon the height or distance and mass of the object. Okay, height, distance, and mass. It is the stored energy of position, right? And then the next second one is kinetic energy. The energy of, we said here, of its position or motion. So this one is the energy of motion. So it depends upon the distance, not distance, speed or velocity and mass of the object. So the total energy is actually kinetic energy plus potential energy. So both these kinetic energy and potential energy added together, you will get the total energy of the system. All right, so you should consider the energy of the position of the object and the energy while it is moving. All right. So for you to understand it better, I'll show you some examples. Okay. So I have this elastic band with me. So initially it's in this position. So I'm using these fingers on my right hand to stretch it. Okay, it is getting stretched. Now it is in this position. And now I'm releasing this. Okay, it goes back to its original position or condition. So what is actually happening here? While I'm stretching it, I'm using my energy to apply a force on this and pull this or stretch it. Okay, so I'm using my energy to stretch it. So what is actually doing here? So I am using my energy against the elastic force of the band and I'm stretching it. Now in this position, that energy is getting stored as the potential energy. Now it's not moving. So what happens to that energy? That energy is getting stored as the potential energy. So in this case, it is the elastic potential energy. Okay. So now this band has the elastic potential energy. So now when I'm releasing it, that stored potential energy is actually converted into kinetic energy for this band to go back to its original position. Right? So that's what happening here. All right? Do you get the idea? Yes. So it is because the potential energy is converted into kinetic energy, it is going back even if I'm not applying a force. Here at the final stage, I am not applying a force, I'm just releasing it. But still, it is going back. What is happening there? The potential energy is converted into kinetic energy. Okay, now this one. I have a ball in my hand, so I'm picking it up from the table. All right. So while I'm picking it up, I'm applying a force. So I'm using my energy to pick this ball up. All right. So now the ball is at this position. Here, the energy I have used is converted into the potential energy of the ball at this position. Now the ball has its potential energy. So now when I'm releasing it, the ball moves down, goes down. Why? Because that potential energy of the ball is converted into the kinetic energy. That's why it is falling down. All right. So in both these cases, we get one idea. Energy is not used up, lost, or gained, but it is getting converted from one form to another. Kinetic energy to potential energy back to kinetic energy. So energy conservation is happening here. Energy can neither be created nor be destroyed. It can only be converted from one form to another. All right. So that idea is also coming at this case. Energy conservation. All right. Did you get the idea? Do you have any doubts or questions based on this? All right, then let's go to the next topic. To understand what is power in case of physics, let's look at these two pictures. So the first one is a racing car, right? Race car. You can see a race car in the first picture. And the second picture, you can see a normal car. So what do you think? Which of these cars have got more power? Which one got more power? Yes, you are right. The race car has got more power. So power is actually how fast work is done or the rate at which energy is released. So race car has got more power because it moves so fast. So the rate at which the energy is released is greater than that of the normal car. Okay, so the power is how fast work is done or the rate at which energy is released. So it is the rate at which. So since it is rate, power P is equal to work done per unit time. Work done per unit time. So what is its SI unit? Its SI unit is watt. Not question mark, question watt. WATT, watt. So what is the SI unit of power? The rate at which energy is released. Okay? Is it clear? All right. Just ask me if you have any doubts, all right? Now let's see an example. Here you can see that a boy is going to kick this ball. All right, he's going to kick this ball. Suppose he kicked the ball with a force of 8 Newton. He is applying a force 8 Newton on this ball. All right, and he kicked the ball. So the ball moves from this position to this position, right? Now the ball is here. Suppose the distance here is maybe 2 meters. All right. And it took 10 seconds for the ball to reach from here to here. So he applied a force 8 Newton and the ball reaches this position within 10 seconds and a displacement of 2 meters. So now we are going to calculate the power. Power is work done per unit time. So how do we calculate work? Work is force into displacement by time. So what is force here? 8 Newton, right? And what is displacement here? Displacement is 2 meters and the time taken is 10. Right? Very easy. So here we get 16 divided by 10, which is 1.6. What is the power, unit of power? What? Here the unit of work is joule per second. Second the time taken. So here we can get 1.6 watt. So the power in this case is 1.6 watt. Is it clear? So it was a very easy question, right? All right. So that's about this class today. So today we have learned 3 new terms: work, power, and energy, and how they are all correlated, right? So work done is actually there should be a force acting on an object and the object should move in the direction of the force. Then there is a work done. And energy, it is the ability to do that work, right? And power is the rate at which the energy is being released. So they are all like interconnected. So I think you got a good understanding of all these terms. So if you got any doubts while going through it, your textbook or whatever you learn, you can ask me in the next class. So that's it for today. Thank you all for listening to me and attending very carefully in the class. So let us see in the next class. Until then, thank you and bye.